characterization of oscillating catalysts by X-ray spectroscopy. The speaker is Liu Jia from the Life Technology and Technology of the United States.
Thank you, Chairman. It is my great pleasure to be back in my hometown to give a talk. I feel even more special to deliver this talk, follow my former teacher, Professor Jia. The topic of my talk today is I'd like to discuss very briefly our recent work on characterization of the operating catalyst by X-ray adsorption spectroscopy. The kind of spectroscopy we do mainly using XIN, which is X-ray near-age absorption spectroscopy, and an XF, extended X-ray absorption fine structure. The work is collaborated with Hans Schroeder of ILI Signal Research and Technology, which is a subsidiary of ILI Signal Incorporated, USA. The work is supported by ILI Signal. For those of us working in the field of catalysis, we all know that the active species in the catalyst usually change rather drastically throughout the catalysis. The oxidation state and the local structure depends strongly on the chemical environment, the temperature, and space velocity, etc. So it is vital for us to understand the structure and function relationship by studying the catalyst during its operating condition. What I'm going to talk today is I'd like to bring two brief examples just to demonstrate to you that how important to characterize the catalyst during its operating condition, and how this will differ substantially if you look at in a postmortem condition. Of course, to study the catalyst under in situ condition facing many challenges. Of course, the first challenge is you have to construct a reactor which simulates or even close to the real reaction conditions. That poses the challenge on the reactor design. X-ray is a bulk technique. It samples the entire sample while you're taking X-ray absorption spectrum. Therefore, you have to design a reactor which ensures the homogeneous dispersion of the sample. Also, through the talk, I'll describe to you how you can actually monitor the performance of the catalyst. Meanwhile, you study the structure. That poses an additional challenge. That means you can only use a limited amount of catalyst, but you have to be able to monitor the performance of the catalyst. Especially in most cases, we have to run catalyst in a differential region. Therefore, most of the time, we have to use a plug flow type of reactor to enhance, to make sure you can generate enough product to be monitored. But there are other requirement which is very special for doing X-ray absorption in the national lab, which is common either in Japan or in the US, I'm sure, same in China. That is, you have to compile, make sure to compile the safety requirement of the lab. The first example I'd like to discuss with you is a CO, the oscillatory reaction of a CO oxygen. CO oxygen under a certain temperature and the CO oxygen ratio, for example, when CO oxygen ratio 1 to 10, and you can sometimes observe a self-sustained oscillatory reactions. This is probably best demonstrated in this chart. While you were gradually reducing the temperature of the reactor, you can observe the production of CO starting from a little bit periodic to become gradually periodic with a large oscillation of the production of CO2. In this case, you can actually see fundamental band eventually the reaction is very unstable with difference of a half degree also. You can actually quench the reaction and have the catalyst become deactivated. This is very interesting. The oscillatory period in this particular chart is approximately 45 seconds. This is actually a very classical problem in the field of catalysis. Many people have studied that both in the single crystal surface and highly dispersed catalysts. Perhaps one of the most significant experiments in this area was done recently by Professor Erdo of Max Planck Institute. What he has done is using a single crystal at 10 to minus 4 torr pressure in a CO oxygen mixture and run a field emission experiment. He has observed that the single crystal surface structure changed during oscillatory reaction. So what he proposed in this case is at the beginning of the reaction, the surface is sparsely covered by chemical oxygen, which is very easy to be attacked by CO and react to form CO2 and leave the surface. With gradually accumulation of CO, the surface is covered by CO, the reaction somewhat gets stopped. Then, at this point, because the high surface coverage, the enough interaction of the CO and the surface will distort the surface and restructure the surface, therefore leaves more room for the attack of abundant oxygen, which will attach on the surface, quickly react with CO, leave chemical oxygen, and deplete CO2. Therefore, the whole cycle started. For those of us working in the industrial catalyst, we all know this 10 to minus torr and single crystal does not represent the true industrial catalyst. Instead, we use highly dispersed platinum alpha aluminum with gamma aluminum or other type of substrate surface, and we operate the catalyst in 1 atmosphere. So, but again, we also observe the kind of the reaction. So it is always to our curiosity to understand this kind of catalyst under the industrial applied conditions. So what I hope to convince you through this talk is in this particular reaction, you actually see the platinum changes oxidation state to change from oxidized to a reduced state and oxidized state throughout the entire oscillatory circle. This is the experiment set up. We put into the X18B of Brookhaven National Lab. It consists mainly of flow controller, where we mix CO and oxygen and send it to a reactor, which is heated by a temperature control heater, and the reactant effluent will send out, which consists of CO2 and some other gas, to a CO2 monitor, broadband monitor, and the production of CO2 is monitored here. Meanwhile, the actual sending through this direction pass in the transmission mode to the catalyst, and absorption of the spectrum was taken at this point. Before we work on the dynamic behavior of this catalyst, we first studied a stationary point. We first put this catalyst in the elevated temperature in hydrogen and reduce it and then cool it down to room temperature. And we took the exact spectrum. And then at room temperature, we flush the surface very quickly. And that way we generate chemical oxygen on the surface. After that, we warm up the catalyst again in oxygen to a high elevated temperature, fully oxidized catalyst. And we cool down the room temperature spectrum. As you can see, the active spectrum shows all three different species are very different. Perhaps it's it's easier to see through the Fourier transform spectrum. In a fully reduced case, you can see a single platinum-platinum interaction peak. Because we're using 3% of platinum in gamma luna here, the platinum loading is so low that you can't really see higher shell interactions in this particular catalyst. Once you put oxygen chem-absorbent surface, you can see the oxygen platinum peak shows up here. However, if you fully oxidize this catalyst, you are not only seeing oxygen peak intensity enhances substantially, also you observe that the peak center frequency, peak center distance shifted slightly downward. That means the chem-absorbed oxygen is slightly longer than the oxidized oxygen, which is not against our conventional wisdom. Unfortunately, in order to take a full scan of XF spectrum, you need more than 45 seconds. Our oscillatory reaction, as I mentioned to you earlier, has an oscillation period of 45 seconds. Therefore, it more or less prohibits us to take an XF at each different point of the oscillatory cycle. So what we did here is we take the advantage of the tonal X-ray absorption. If you look at the full XF spectrum of oxidized spectrum and reduced platinum alumina, you can see the main difference really is showing this area which is called the white line region. You can practically hold your X-ray photon energy right at this point, and you lock your photon energy at this point, let the reaction oscillate. You just follow the fluctuation on your X-ray intensity, and this is what we obtain. Indeed, when we make the reaction oscillating, we see that the intensity of this white line intensity also oscillating in between a fully oxidized and a fully reduced by CO, which suggests that during oscillatory reactions, the catalyst is actually partially oxidized and then partially reduced, partially oxidized, reduced, and follow the entire circle. The beauty of our experiment setup is not only allow you to monitor XF, but also allow you to monitor the product. We overlap the two the two data together, as you can see, that they are exactly correlated, even to a very small point of the fluctuation. So what this indicates to us, besides what I've told you already, is the catalyst fluctuating between the fully oxidized, between partially oxidized and partially reduced the cycle. It also tells you that the production of CO2 is exactly related to the oxidation state of the catalyst. If you look a little bit more carefully here, for example, let's just expand this region slightly larger, you can see that during the adsorption circle, where the production of CO2 is somewhat attenuated, the white line intensity also decreases gradually. The decrease is gradually. But once, for some unknown reason, the catalyst gets ignited, and there is this explosion of the formation of CO2, meanwhile, what you see in the white line intensity is jump right back to the oxidation state. Thus far, I tell you the experiment result. The question is, what exactly initiated this instability? This is the question we have to be able to answer. And another question obviously leads to the experiment. Compare this experiment with a single crystal surface is what generates this coherence between each single microcrystal. Remember, we're discussing here is a highly dispersed platinum on a common inner surface. We're talking a collective property of each single crystal. However, for some reason, they behave coherently. This cannot simply be explained by the surface experiment. In the surface experiment, Erlo has proposed that the surface reconstruction can propagate on the surface very fast, but you cannot using that kind of explanation to demonstrate the real working catalyst. So this indeed remains a puzzle for us for the future study. And also we have some interest to study exactly what the accept looks like throughout this single redox cycle. As a matter of fact, we have made some significant improvement. We're using currently so-called energy dispersed accept, which you can take a spectrum in a couple of seconds. This is a decent signal resolution. We have already taken a full spectrum of single circle. It shows that indeed there's a mixture of oxides. Due to the time constraint, I wouldn't be able to discuss that part of the experiment. Okay. I'd like to jump to the next experiment, which is a relatively hot topic nowadays in the environmental catalysis. NO is known a carbon acid gas and is detrimental to health and environment. Until recently, there isn't any significant efficient catalyst to cure this problem. Yamamoto and his co-worker recently published a result to show that copper exchange over exchange CSF5 can decompose NO to N2 and O2. We also run this experiment and for various reasons it shows that this catalyst is really unstable and easy to deactivate. So the commercial future of this catalyst might be questionable. However, it's still interesting to understand the reaction mechanism of this particular catalyst. Of course, for catalysts like that, there are always a different kind of mechanism proposed for this particular reaction. But actually one of the most interesting experiment, complete experiment and mechanism was conducted by Ling and Hall of Pittsburgh University of Pittsburgh. They demonstrated, or they proposed the so-called redox mechanism. In this mechanism, they suggest that there is active site in the ZSM5 where NO can absorb on the surface and form some kind of transit intermediate species. And this species will further decompose to form N2 and oxygen attached to the site. The site will be able to regenerate itself by desorption of oxygen, and they actually postulate the sites are due to a glucosign. To support his conjecture, Hall and Lee run several experiments. One of the experiments is they actually run the oxygen desorption rate on this particular catalyst and compare with the NO decomposition rate of this catalyst. And they say they find really good correlations between the desorption rate and NO conversion rate. Therefore, it's supporting the mechanism that glucosign is indeed responsible for the decomposition. For us, we feel like there are many more questions remain to be answered. First of all this experiment thus far was defined by FTIR-ESR microbalance experiment. These are either false in situ experiment, or they were using some certain kind of messenger molecule, such as NO, to postulate exactly what's happening to the glucosign. We feel that XF or zinc in this case can provide a direct approach to look into the copper species, and during actual NO decomposition reaction, and therefore we decided to run this with our similar kind of in situ setup, except in this case we're monitoring the NO decomposition rate instead of the CO2 formation rate. First, we run this catalyst in a pure helium according to so-called decomposition reactions. You can actually form cuprous That way, indeed, we see a peak gradually grows in with increasing temperature this peak actually is assigned to Cooper's ion 1s to 4p transition. And we actually use a simple fitting mechanism to show that this carbon, under this kind of a spectrum, before there was about 70% of Cooper's ion existing, under 50% exchange copper ZSM5. However, after dose 1% of NO in adequate temperature, 500 degrees centigrade, immediately you see a decrease of this signal. But this decrease by no means shows that Cooper's ion concentration is eliminated. On the contrary, if you're using the same fitting routine, it shows you that there are approximately 25% of Cooper's copper ion still in the form of Cooper's ion. Inspired by this discovery, we just run the whole NO decomposition in a temperature circle, starting from 500 degrees, 600, back 500, and then 400, 300, and then back. We see that this peak intensity indeed depends rather strongly on the temperature. In fact, this is a better way to look at it. You can see that indeed, for these three peaks, they're all in 500 degrees. They basically return to the original peak intensity. In fact, as I mentioned to you earlier, we are able to monitor the decomposition reaction and study the zinc simultaneously. So we put on this transparency here, the plot here, the normalized Cooper's ion age intensity, or you can interpret that as a fraction of Cooper's ion, whereas the normalized NO decomposition rate. We find relatively good correlations between 500 degrees to 300 degrees centigrade. And there is indeed some discrepancy at 600 degrees. Actually, if you look at it, this is another way to plot this particular chart. We also take in this chart Lee and House where they measure the decomposition rate of oxygen. You can see that they are indeed, all are relatively correlated with each other except at an adequate temperature over 500 degrees centigrade. What we attributed this is indeed Cooper's ion is responsible for NO decomposition. However, there is a key difference between our experiment and Hall's experiment. Our experiment represented true dynamic balance during the reaction conditions of the Cooper's ion intensity, instead of Hall's experiment, which corresponds only half of the reaction. At adequate temperature, the discrepancy is not very hard to understand. With the increase of temperature, you always generate more and more Cooper's ion through the desorption. Remember, another half of the reaction requires adsorption of NO on the surface. NO will have a hard time to adsorb on the surface if you unlimitedly increase your temperature. I think that's where the negative dependence of temperature is. I think my time is up. Thank you very much for your attention.
I have a question for your first part of the talk. Was there any preferred surface orientation of the reacting particles in the vacuum catalyst using the XDS method? Any preferred surface orientation?
Preferred surface orientation. XF cannot really tell you. I can't answer this question through XF study only because XF